Hi guys, welcome to another masterclass. Thank you for joining us again. This is going to be the last one that we do before the summer break, so let's be real, we're going to be working our butts off. We do have a lot of people that we've talked to offline with regards to their specific questions, so keep that coming. Thank you so much for doing that, and I hope that we can just help, genuinely help. So if you want to book a session, that is the link for that. And yeah, we're just going to get started with what we're talking about today. So today we have Stuart Jackson joining us. Stuart and I have known each other for quite a bit of time. Stuart used to work at EOS, and that's where we met first. And I really have always appreciated his mentorship. He's a very well-balanced guy. He's very careful with his words, and so I'm going to put him on the spot today with regards to multi-laser systems. Stuart is now at Renishaw, where he is supporting all the efforts on the additive manufacturing side, specifically with the 500Q, which is a pretty cool machine. We're going to get into that, but keep in mind this is not a product placement ad, so Stuart is going to have to answer some tough questions. And you already know me, of course. So the first thing is we're going to, again, have a 30-minute theoretical discussion about some of the topics, and then Stuart is going to give his insights on that. You can ask questions at any point of the talk. Just please feel free to send it in the chat, and we'll answer it as we go along if there's something not clear. Now, I did get a lot of questions, again, from you guys through LinkedIn when I reached out, and thank you so much for that. It helps me calibrate everything that we're doing. But also what's really important is that it gives us an idea of where you guys are in your thinking. And so, these problems have been solved, so we can definitely help you with all of that. So again, if you have some of those questions, go ahead and book a session. We'll try to answer as many of them as we can, because I do have to admit that, again, what's happened is that a lot of the questions are very in-depth. So I tried to boil it down into the essence for the conversation here. And if you would like more information, along with the theoretical content that we're going to present, it's a lot to go over. Okay? So if you would like to have more information, just feel free to book a session. That's not a problem. It's a free consultation, and we'll try to help you as much as we can. So the first thing we're going to talk about are the quality aspects of multi-laser systems. They're not easy to deal with, and that has to do with the qualification as well, which we'll get into a little bit, and then the economics. And then we're going to talk to Stuart about his experiences, especially at Renishaw and at EOS, of what he's been working on. And then there'll be a Q&A to go. That always rolls, 10 minutes. It might go a little bit longer, but we keep it down to 15 minutes. So the first thing I wanted to talk about is when we discuss multi-laser systems, we have to talk about the deviation in the optics. And that's because everything in these systems is based on a very, very delicate coordination between the different elements of the process. So we have what's called a beam splitter, scanner, and the lens system. And the reason why I'm talking about the f-theta lens first is because this is a more stable, simpler arrangement. The same problems that you have in the f-theta system are the same problems that we have in the variooptic. And as you can see in this diagram, what we're trying to convey is you have the laser that is converging onto the powder bed, right? And what happens is where that point converges is the thing that we're trying to control. Now, a cubic centimeter of material in the process is equivalent to about 250 kilometers of laser trims. So anytime that goes off, that is a huge problem because that is a quality issue. We see that in porosity, we see that in surface roughness. And each one of those elements that you see here causes deviation in the X and Y position of the build, and then also in the Z. So in the way that the laser is not focused at exactly the building height that you have. So you can see that there are some issues with the decoder, which is a very fundamental problem, and we'll have a masterclass about that as well. But there's very large deviations from the lens itself, which are thermal deviations that then cause deviations in the X, Y, and the Z position of the laser spot. There are deviations in the scanner, which result in deviations in the X and Y position, and then the beam splitter, which is the thing that is actually splitting the laser beam so that it doesn't fry your electronics, and then it converges onto the build, because otherwise the energy source would be too dense. Now, we talk about this because of a very fundamental, like if you understand these principles, you'll be able to deduce a lot of things in your process, and this is why we focus on this in the theory. So the challenge with all of this is that when you're calibrating these systems, you have these deviations, and as the system is being calibrated, the system considers when you're doing a focus monitor test, when you're doing an X and Y positioning of the laser, what happens is that the laser is actually heating up the elements so much that there's a shift in the Z position, right? And this is the way that we're calibrating. So as we're measuring and we're adjusting the laser, what we're doing is we're doing it in a fashion that the optics are heated up. And the optics in that case are heated up in a way that is unrealistic from the process. So we have these two calibrations, which we talk about in our trainings, which are called the static and the dynamic measurements. Now, as you're building, that is a dynamic process. The laser beam is constantly moving throughout the lens and the optics, and it reaches equilibrium. Of course, every time the laser beam is turned off, the optics and the elements start cooling down again. However, when we're doing the calibration, it's actually in one spot. And what happens then is that as the optics are heating, the Z focus shifts up. And so you never have a real true Z is equal to 0 on the build height. And then the second thing that happens is that there's a lot of distortions of this Z focus as well during production because of the splatter and the pollution from the production itself. So these are two things that we don't consider on a regular basis, and this is something that you should definitely, whatever machines you're working with, you should definitely question, even on the single laser system. And so, of course, during production, as we're building, there's smoke, and then the role of the gas is to prevent the parts from catching on fire, of course, but also, more importantly, that flow has to be as laminar as possible, which never is, by the way, no matter what anybody tells you, in order to make sure that the pollution is going away from the laser, because every time that the pollution gets in the way of the laser, it shifts the Z focus. So we take a simple example of a single field, small machine. And what happens is that we have a very predictable gas flow, and we have laser paths that cover the entire build area. And now what happens in this scenario is that the laser and the gas flow has interactions, but those are quite relatively easy to manage. The first materials that were started with was like aluminum, and we didn't really see a lot of issues with that because of the fact that aluminum is not a material that causes pollution that actually affects the laser path. So it's very insensitive to that, and that's one of the reasons of why when you see new machines being released, one of the first materials that are available is aluminum, because that's the easiest one to actually develop. When you get into issues, when you get into alloy classes like super alloys or steels or titanium, those are materials that are a lot more sensitive to the process, and those are the ones that are a really good benchmark to understand whether the machine is good in performance, and to also understand which flaws the machine has because of the fact that the materials that they release and the density and the properties that they release. So this is a diagram that actually shows both the Varioscan and the F-data lens, which actually can be put in tandem, and they are on certain systems. We're not going to get into specifics on certain systems because, we're going to be speaking very honestly here. So when we talk about an F-data system, right, we have this lens, and then we have the scanner mirrors. And as the laser beam hits the scanner, there is this radius that it sweeps across from the extremes of the build area. And so that distance between the scanner and the actual build platform is changing. And so that's what the F-data lens does, is it compensates for that in order to make sure that as we're sweeping along, that the distance to where the laser is focused is actually constant and it's planar, right? So it's resolving a radial coordinate to a planar system. And of course, that is a lens that is heating up, and we have to make sure that it's cooled, and we have to make sure that the smoke is being removed. As we have these lens heating effects that we mentioned before. As we get into a vario-optic system, it actually gets more complicated. And so there are positives and there are negatives. So the first thing is that calibrating a vario-optic system is a lot harder, because for every step that you're changing the radius, you have to calibrate the system. And like I mentioned, it's very difficult to do because of the fact that when we're doing a static test, it is not representative of the dynamics of the system itself. So the vario-optic system inherently will be, if you consider a very simple example, will be more difficult to get the same accuracy as an F-data system. However, when we get into multi-laser combination, it actually has its benefits, and we'll get into that in a second. So the reason why a very optic system is beneficial, it has to do with the laser overlap, right? So there are systems like this one on the left here, which have 4 fields and they have a slight overlap region, or they will have 4 fields in a line. And those overlap regions are really a pain in the butt because each one of those corresponds to a different lens. Now, as those lenses have different losses of energy, you have to calibrate each one of them individually. And of course, as I mentioned, that is a static calibration, not a dynamic one. So even though you've statically calibrated things, dynamically, the system will be behaving differently. And that's a problem in and of itself because of the fact that then the overlap is going to be mismatched because lasers will have completely different Z-focus positions. And that results in an X and Y miscalibration as well. So generally speaking, you will never have the same quality of a part that is built across the entire build as you would if you were to build it in a single laser system. So that's a big minus for multi-laser systems in general, and this is why I always question the productivity of them. There is, of course, less pollution with an overlap that looks like this because the lasers are not interfering with each other as much. But the difficulty in aligning is a really big cause for concern, especially with, for example, titanium, which has a very sensitive behavior when it comes to the alloy properties. And there's a loss of productivity when you have asymmetrical builds because at a certain point, one laser will be running, another laser will be running, and then one will turn off first, then a second one will turn off. Those lenses are cooling and then deviating again, and then while the other ones are still running, and you have an inherent loss of productivity. Now, there's the other combination, which is the full overlap. And the full overlap is fantastic. That's actually how the 500Q is. However, the challenge with that is that it's a more delicate dance between the individual lasers, which is causing issues if there is pollution, because that has to be whisked away and not go into the direction of the other laser, because that will actually cause a Z-focus deviation, which, just for your information, if you have a 2 millimeter deviation of the Z-focus, the energy density is decreased by 30%. It's a really big deal. So there's a loss of quality in that respect, and then also because of the fact that all of these lasers are working at the same time, it's not the same thing as a single field laser, because of the fact that the heat input is 4 times as intense. So if you think that you can just transfer one process from a single laser machine to a 4 laser machine, you're very mistaken, because the heat input is different, which means overheating, which means that we have to develop completely different process parameters. So the second aspect that we have to talk about is the gas, right? And this is what I mentioned before. There are certain systems that are elongated and the gas flow is very stable, like the single field system. And the short distance of travel means that the gas is a lot more stable, right? However, the large parts are not possible because unless you have, for example, an engine, right? Then there's a second kind, which is the larger systems that are square. And the problem is that the gas flow takes a lot longer. And so as the gas flow is progressing, there is turbulence. And the thing that is a big issue with these systems is that what we call base loading. Base loading is the principle of how many parts you're exposing at the same time on every single layer. Because as those parts increase, the number of splashes increases, which land on the part, which means that the number of defects within the part actually increases exponentially. And finally, we have a third system, which I always kind of wonder where this came out of, but it's a system where the gas comes from the top and then it goes up sideways. And the problem with that is that gas is like an electrical circuit. It always takes the path of least resistance. So even though the gas is coming from the top and it should be going out sideways, it never actually successfully wipes away all the pollution. And so this is a very inefficient and poor quality system when it comes to heavy alloys, such as super alloys or steels, because those particles will actually fall right back onto the part, and there's a lot of laminar flow issues, which cause defects in the geometry. So, it's not that these things are not qualifiable, but the quality will not be the same as a single field laser system. So that is kind of what we use as our reference point. So then I kind of wanted, from these basic concepts, I think you can deduce a lot of things on your own. And what I wanted to point out is kind of like, what are the benefits, right? And all of these benefits, as I mentioned here, the gas flow, laser, Z-focus, interference of the laser, gas and laser interference, overall part quality, and the difficulty of qualification, can also be looked at from the perspective of what kind of alloys are you focusing on. And there's these two extremes of super alloys and titanium. Titanium is a material that is not sensitive to pollution. However, it's very sensitive to the laser path that is being taken. Super alloys are not very sensitive to the laser position. However, they are very sensitive to pollution. And so when you take a look at a single laser system, for relative comparison, a small single laser system, all of these are kind of the best, right, relatively speaking. When you take a look at the other systems, this is what we see. So the biggest weakness in a multi-laser, small laser system is the laser interference. The biggest issue with a multi-laser in a large system with a small overlap are going to be these three categories of gas laser interference, part quality, and qualification efforts. And then a multi-laser system that is large, where the lasers are totally overlapping, those issues can be even more compounded in terms of the challenges that you will face during qualification. And also take a look at it from the material side. What do you want to do? Because we're noticing that these niches are developing, and you have to ask yourself, what kind of system am I going to get, and what materials is it good for? Because it will also dictate the business case that I have behind the production efforts that I'm doing. So I do believe that that is a pretty good introduction. I know that all of you have a lot of questions with regards to these specific tasks, like how to optimize the laser paths, how to calibrate the systems. So just book a session. We'll talk about it. I can give you all the tips on how to do that in terms of best practices that we've learned, because we've gone through qualification of these systems for aerospace. So we are talking about, the high level qualification. And then on the capital side, like, the economics basically dictate that, you need to have new investments in the facilities, because of the fact that these larger systems or multi-laser systems have completely different requirements. On the capital side, we need a lot more powder. We also need to do a lot more testing and validation. When a job fails, you have to remember that now you're not losing a small build, you're losing a large build. So the costs are proportionally expensive for the losses, so the risks are higher. And quite frankly, lasers is not the answer to productivity, because when we talk about productivity, we talk about the cost of the systems and the speed. Now, of course, the speed goes up, but so do the costs. And so one of the things that I always say is, if I was to have a metal AM machine that costs €1, $1, I wouldn't be asking for 4 lasers. I would just be focusing on that, because, of course, my productivity is directly correlated to the cost of the part. I really wouldn't care if it takes 3 weeks versus 1 week, right? So that is something really to consider. And then finally, the part quality is reduced. And so we have to accept that inner qualification. We have to accept that in terms of the applications that we focus on. But realistically, if you're building a large geometry, you don't expect the same kind of quality for most parts as you would from a small geometry. And then process efficiency is inherently lower. The theoretical for 4 lasers is 3.5 that of a single laser system. However, it comes out to be around 2.5 or less, and we're actually releasing a study on that. So that'll be coming up soon. So it's really important for your business case. So now it's Stuart's turn. I do hope I didn't ruin any surprises, Stuart. Please take it away, and yeah. Thank you.
I'll start by questioning you on one thing. You put a very strong favor there for single laser systems, and I've had a lot of experience on those, especially in terms of qualification and the part status. But actually, my experiences, and I've got this in the slide, single laser systems from different suppliers will give you different part quality across the build area.
Absolutely. But I wasn't getting into into individual manufacturers' requirements, right? My point is that just from the purely theoretical side, and I know that it's a very absolute thing that I'm talking about, right? But from the purely theoretical side, if you have 1 laser versus 4 lasers, you have 4 times the headache. And actually, it's more than 4 times the headache, because the challenges are exponential. And I think, honestly, Stuart, I honestly thought you were going to go in a different direction, which is for the 500Q, because of the fact that you guys can actually turn off some of these lasers until people are ready to use more.
Yeah.
So
absolutely.
So there's a pitch for you. Okay, that's all you get.
Yeah. Okay. Excellent. I'm going to go over. I've got a small presentation, if it allows me to do it. Just got 4 or 5 slides here, really just to set the position of what we're talking about. So just to recap here, we do single laser and 4 laser systems in the 250mm by 250mm area. So what you're seeing here is a video of our Galvo block. That's 4 lasers working simultaneously, able to touch every corner or every part of the bed there, which is great on one hand, but as Matt has pointed out, adds new problems and difficulties that go with it. So just showing through. So heavily involved in a lot of qualification processes, and the quad laser, or this size of machine, the qualification process adds another level on top of maybe what's been going on before. One of our customers calls it boring repeatability, and reliability is the thing that they're after beyond anything else. And once you add 4 lasers in there, depending on how you want to apply that, whether it's 4 lasers on a single part, whether it's per individual laser, there are different processes to go through, and there are definitely different effects. One thing that we focused very heavily on was, and I've got a couple of slides here that show it, is what I would call clean chamber processes. Partly that's about gas flow management, and that's learned with pain from earlier systems that we had on the market, legacy systems. So what we have with our system is, like so many people, we have this laminar flow working from the right side of the chamber to the left. But more importantly, we have a mass flow of gas coming down from the top of the chamber. So we have a perforated ceiling around the single window where the lasers are all being sent through. And that one has probably the biggest effect of actually keeping the gases down. And then combine that with the way that we scan, the way that we share data in terms of how to make this work, we feel that we're in a good place to be able to go forward. This is sort of taking a demonstration of what the value of that, and it comes back to what I was saying earlier on a little bit to Matt, the differences between single systems and multi-laser systems don't necessarily correlate. So on the right-hand side, what you've got there is data from one of our legacy systems, so our older systems. And you'll see that we've got quite a broad range. If you look at the yield values, the range, these are 6 locations around the build area in that 250 millimeter area. If you look at the standard deviation values that we're talking about here, and that is because parts of that chamber were definitely not working as well as other parts of the chamber. And honestly, we're not the only ones in that area. But these are machines that were designed and built through the 2000s into the early 2010s, and the knowledge base of what the impacts of this were much less. If you move over to the left-hand side, you'll see the values for the René M500Q. So bottom right figure, if you look at the picture and down by where it says Renishaw, you'll see that the configuration of the test build. And then if you look at the standard deviation on yield stress, this is down now to 6.2. So significant differences in terms of that, and of the difference between a legacy system and a modern system. And you'll see here on the graphs at the bottom, the consistency of build relative to all the different places in the chamber. This is something that we're now finding is to be a significant thing. Now, this isn't only about gas flow. If I move on to the next slide, it is also about the way that you have to process and plan your parts. One of the complexities of having 4 lasers that can go anywhere is balancing the effect of one laser upon another versus the economic targets you're after, which is maximum productivity. And what we found, and again the slide will show it afterwards, where we've got lasers working very close together, we're finding virtually no impact from one laser to the other. Where we have a larger distance, that will play again, a larger distance, so these 3 lasers, and then we've got the 4th laser working over here, gas flow is working from the right side to the left, the impact upon properties, surface finishes and everything is significant. So balancing that against your scanning strategies and how you want to make the most of your productivity is significant. And there you are. So the effects upon, in this case, ductility and UTS. So the charts show here the downward distance, so the distance coming along and the effects upon it. So where we've got a greater distance, we are seeing much more difference, a significant difference in the mechanical properties, depending on the materials, because of that distance. Where we're working close together, we see negligible difference. Okay, so that's all I've got on the slides.
So Stuart, I guess just to jump into it, I don't want to waste time. One of the things that we talked about is whenever we're doing these kinds of tests, it is very important to consider what is the material that we're working on in terms of appearance, and then the second thing is how have you quantified like how it affects a different alloy in terms of base loading, right? Because as the area of exposure is increasing, then the number of defects increases. This is kind of known across the laser powder bed fusion side. So I'm just wondering if you've taken that into consideration, because of the fact that I've seen in your build that there were a lot of tensile bars, and tensile bars can be misleading because of the fact that it's a very small exposure area, and so there aren't standards to this, and so I can make the data look good or bad depending on the day of the week. If I'm hungover from partying on the weekend, I'm going to make it really bad. If I'm having a great time and I just want to get on with my work, I'm going to make it look really good. Yeah. So what are your thoughts on that?
So the first thing I'd say is that one of the significant things that we're seeing, the question about how you apply this. So people that are moving to this technology generally already have a single laser system. So the learning curve that people have gone through has been significant. They've got the basics in place. So when we talk about things like qualification, for example, most people that are coming to the table at the moment are using our machines as 4 single laser systems. So the qualification process is very similar to what you would have with a single laser system. And that is by far the cleanest, fastest way of actually achieving results. And it's what you get there. If you've got the right numbers and you've got the right quantity in there, you can actually get very good efficiency and very good productivity improvements from it. If you then move to single parts, where you're talking about, that's a much bigger complex thing. And that's still a stepping stone at the moment. There are a limited number of people that are actually using a smaller, larger multi-laser system to actually produce large parts. Thick sections with large parts, actually not too difficult. Thin section large parts are proving far more difficult. When we're talking of sub 0.5 millimeter wall thicknesses, having that alignment and connection between each of the lasers is very much more demanding. And there's still work going on there. I wouldn't say that we've got that cracked to a satisfactory level yet, but there is R&D work going on to it. So trying to answer that, there are 3 different perspectives that we have to apply to this system, and depending on which one you look at, it's either relatively simple or it's very difficult.
Mm-hmm. Tell me though, to add to that, right? How do you manage the complexity of the fact that these systems are black box, right? And that's just generally speaking across the board. You and I have touched up on it, but I have one other point to mention to that, which is that when we have these black boxes, right, we can say as a counter argument, well, don't worry, we're gonna give you access to everything. The problem with that is that I've noticed that, for example, some of the machine manufacturers whose names we won't mention have been extremely successful because of the fact that they lock down the parameters. Yeah. And because those parameters are locked down, people can get on with their work rather than tinkering around. So it's a very fine line between we want to give people access and control to this, but we know that they're just entering this industry. They're not experts, even though they might say they are. They're not, and that complexity overwhelms them. They start focusing on things that are not helping them, and they actually do themselves more harm than good by doing process development on something that should be working, right? Because there's still a lot of other bottlenecks afterwards, after you figure that stuff out.
Yeah, but parameters are very much need adjustment and setting relative to geometry. If you're looking at it properly, people don't buy a 500Q to play with. They've got an intent, they've got a purpose behind it, and normally they've already got a part that's in production on either one of our earlier platforms or somebody else's platform. So there's a much more different approach. It's not a general purpose approach. And I think that makes a big difference because it means that you go through that proper production engineering first setup phase that's going on. Our systems are open architecture. From a philosophy, anybody who's seen the Mark Saunders presentations that have been out on LinkedIn at different conferences over the last couple of years will know that we're very open in sharing the information. So, for example, the the downstream gas information, rather than lock the system out to stop people from having that problem. Our approach is to supply papers out that actually demonstrate the effects of what they are. So it's a very different approach. So bottom line, we'd rather supply the information for you to make judgment. This isn't for a guy who's buying his first machine. This is for a guy who knows what he's doing.
How many of those people are out there?
Surprisingly a lot. And it's interesting actually where it is difficult. I agree with you. I mean, it's in terms of maturity, what we're finding is that we've got people that are that have honed a process. I was in Florida not so long ago at a medical company that have got another manufacturer's machines. They've got that process absolutely perfect, 2 of those smaller machines, and they've converted over to a 500Q. Amazing company doing fantastic things. We benefit in the sense that they've already got that process working really nicely. And that meant that when they converted it over to our machine with a little bit of help, and we're talking a little bit of help, it's worked absolutely superbly. If I look at your comment about
what was the application? What was the application in that area?
Medical implants.
Okay. And now, have you seen that
titanium
the case for all applications that you see, or like you mentioned, thin walls? But what about other quality aspects that I think people have to watch out for before they go, let's buy a multi-laser machine? We can just turn them on later on.
Comment on thin walls only applies to thin walls on large parts, where 4 lasers will be working one single geometry. That needs another level of self-calibration within the machine to really work, whether it's us or whether it's anybody else. Because the current processes of establishing the calibration is still very much a manual process. And you know how that works. Even in my old days, it's down to what service engineer comes in at what time and how much beer he's had the night before. So there's still an influence going on there. So there's elements there that have got to get better and better. So yeah, in that particular context. One of the comments you made earlier on about, there are some people that sort of lock the parameters down, lock the systems down. What I would say is that the big drivers in the industry, the big aerospace companies, they're not prepared to have that. They're not going to buy into it. And in truth, those are the people that are going to influence the rest of the market.
I agree. Yeah, I've definitely observed that. I think maybe some of the audience might even comment on that because I think they've experienced that themselves. But now, what would you say would be a good application example and a poor application example for multi-laser systems transferring?
I can't give a specific geometry, but if we look at, we can't because of the confidentiality. I mean, the thing is, coming in where we are in the market with this system, we're working with people that have got very confidential projects that are tied up on NDA. But what I would say is, if you take a medical implant of sorts, whether it's a spinal cage or whether it's an acetabular cup, you can see productivity gains. One thing that was very interesting on thicker section titanium parts, when we built those parts on our older systems, we found that there was residual stress cracking quite significantly. And what we found out particularly was that they were generated by flaws that were generated, as you rightly said, by the gas flow, by the condensate getting embedded into the melted part, therefore producing a crack propagator. What we found with making those large parts with bulky sections, we're not talking about thin wall sections, on the 500Q, the 4 laser system, we were able to build them without those cracks. And when we analyzed it, what we found was that the combination of the way that we're managing the scanning process, so we're taking into account the downstream gas effects, and the fact that we're managing the cleanliness of the chamber, we were not getting those flaws at anywhere near the level within the builds and the parts we're completing and managing it. That's a much bigger issue. People miss that point. I have a customer that's got another system, same size machine. It's got a 250 size machine with single laser. It doesn't matter who they are or what it is. One of the feedbacks that they gave me was that they build a particular part. It's a small part, 25 mil diameter, probably about 40 mil high. On this other system, they build around about 50 parts in a chamber. When they moved over to the Q, the 500Q, which they managed to build 100 parts in half the time.
Mm-hmm.
But my question
What
was,
material was it?
that was an Inconel. That was an Inconel material. What was significant for me was that I went back and said, well, that's great, but why aren't you building 100 parts on the single laser system? Because it's exactly the same build chamber. And the feedback was that we know we can't. We've tried to. And the effects of downstream, or the gas effects into the quality, means that those parts will not succeed. So effectively, through the quality improvement from the gas management, from the clean chamber benefits, combined with the productivity gain, you were close to 4 times productivity. You know you're not going to get 4 because the amortization of scanning, etc. in there, and you've also got to optimize that you get all 4 lasers working simultaneously at exactly the right time, and that's very difficult when you have changing geometries.
Well, I'm still not convinced after this talk, by the way, of why I should buy a multi-laser system. Because at the end of the day, as you said, there's a lot of optimization that you can do. What's the point of the optimization, right? Like, you do have the risk of, setting that up. A lot of people dedicating a lot of their time to do that, right? So why not focus on everything that you can build on a single laser system on that, and then focus on things that you need a multi-laser system for?
So taking a single laser,
where do you cross the line? Like, because the people doing their business on a day-to-day basis, they need to have a rule of thumb approach, right? Because otherwise they're going to throw everything on one or everything on the other, because they just don't want to deal with the other systems.
So you've reached your capacity level on a single laser system. Where do you go? I mean, one of the key things is that you tend to go for a bigger system. That's an option. There are a lot of companies, especially in the States, that have done that. However, as you pointed out at the beginning, the infrastructure investment is substantial. I supplied the first 4 laser EOS machine in the UK to Material Solutions back many years ago, and seeing them move from their small.
I think everybody's heard that. Buy EOS.
No, absolutely not. But I'm just saying it in the context I have experience on both sides. But the point I was making there was, once you go to a large system, the infrastructure, your building infrastructure, is significantly changed. So if you want to improve your productivity, a same size system which allows for the same kind of handling. At the end of the day, when you open a chamber on a 500Q and you're handling the powder and you're handling the chambers, the build plates, etc., at that point, it doesn't matter. We offer the machine as a single laser or 4 laser. It makes no difference to you. The only difference is the fact that the parts are coming off a lot quicker.
Mm-hmm.
That's the significant difference.
That's a really good point, right? But now the question is parts are coming out within a week anyway, right? The aerospace projects that we work on, they have, manufacturing times of 3 weeks, right? So yes, great if we can cut it down. The challenge is that this is a completely new process at this point, and we have to requalify it, right? The energy input is the same. And so it's not just, turn it on and deal with that. But because of this confusion with the black box, because of the frustration of the fact that we have to validate a completely new process, because we have to understand the interference of the lasers with each other, along with the smoke, I'm leaning on, I would just want to focus on having 5, single laser systems, unless I really need the bigger thing, right? Because like I said, you got these 4 lasers. That's great. It goes faster, but that means that more people have more work to do. And right now, the impression that I'm getting is not that they're having capacity issues, right? Most manufacturers right now.
And I'd agree with that.
I don't take that one away, okay? Because that's not a fair judgment. It's a very special time right now. But generally speaking, how do we square that out?
We're seeing it because I think that the people that are showing extreme interest in where we are have got much higher intentions. They're not going into the existing pool in the way that other people are. They are thinking. I know one company I'm dealing with that is completely off the radar of everything that's going on here, and they have intention for lots of parts, and they are small parts, and they make sense on a multi-laser small system. I mean, economics are quite significant. You put 5 systems in, or 4 systems versus a single system. If I just do the simple economics, 4 lasers working on our machine as a nominal list price, say, of $1 million for a machine. So each laser effectively is $250,000.
Right.
Who's going out there and selling single laser $250,000 machines in the market? I mean, Maybe it's getting close in certain areas, but generally you wouldn't do that. You wouldn't have it. Also, gas consumption, the powder management. You're dealing with it in one system. It's a nice stepping stone if you've already established a production process on a single laser system.
So what it sounds like to me, if I was to kind of like coordinate this, right, the first thing I would do is I would get single laser systems, keep going with single laser systems until I realize that my operational capacity is limited. And then I would switch to, literally throw out those machines or put those machines to another project and then move it on to 1500Q.
So the balance there is that we offer the 500S, which is exactly the same machine with single laser. And subject to how we develop it, we were offering that originally that you could have that upgraded to 4 lasers.
Got it. Okay. No, that's a very good pitch. So the big challenge for you guys right now is to get a larger machine out there, right? Because that's, I guess that's to kind of like summarize, right? Because we're reaching our time limit. So the first thing is if you have a big application, obviously you need a big machine.
I think at the moment, the secret for us at the moment is to focus on what we have and find those areas that would benefit the most from what we have. That is the focus. That is what we need to be doing, and I believe that's the way forward for us. We're not everything to everyone. We've got a production machine that is intended to do a specific thing. It's let's call it a sports car. We're not going to use it as an SUV.
Understood. Awesome. Thank you, Stuart.
And
sorry for the pushing you a little bit.
I'm used to it. I've known you long enough.
I know. as long as you're happy to come back and talk about some other topics next time.
If there's an interest, definitely, yes.
Thank you. All right, guys. Thank you so much for everybody to join. Like I said, we're going to take a little bit of a break for the next 2 months because we do have a lot of work. There are some of you that have contacted us with regards to the Optimo, and right now we are really full with that in terms of supporting people that are using it. So you can just send us an email to the Masterclass or to one of our personal emails. And and then one other thing I forgot that Kate just reminded me is, if you need to talk about anything technical, just set up a session and we'll give you free advice in terms of how to deal with your problems. And then if you need Stuart's contact info, you can definitely reach out to us as well. We'll pass that along. Thank you, Stuart.
Thank you.
Thank you. Cheers.